Well, my name is Kasir Pandey. I am assigned this topic generating functions. Writing generating function means we write a compact notation for a series or for a sequence of the algebraic terms. Like here we are given a series. So the series contains infinitely many terms. It's not possible to write all the terms at all time. So as we here even we have written dash dash means we have excluded a large number of terms here. Even after that, while doing calculation and other all the time, it's not possible to write these even. So what we do, we have a way to encounter this problem. We just write compact notation. This can give any value, any factor corresponding to value of n. So if we need a2 x2, we put here n equals to 2. Like that, if we need n equals to m, we can put here m here. So we can get all the terms with this. We don't need to write this at all. So similarly, if we are having a function like ax equals to 1 plus 2x plus 4x squared plus 8x cubed plus 2 raised to m and xm up to infinite, still there are infinite terms. We can't write all the terms. That's why we have written this dash dash. We have excluded those terms, but they are not a lazy number. There would be a large number of terms. So as this is not possible to write them, we have written this dash dash here. So even after that, we have excluded large number of terms. It's not possible, and it's very complex to write like a series all the time during the calculations. So we do follow the procedure as I'm explaining. And similarly, we can see here if we expand exponential x, then we will get the terms 1 plus x over 1 factorial plus x squared over 2 factorial plus x cubed over 3 factorial x n over n factorial up to infinite terms. We can't write all the terms here. So we can also write this, write a generating function corresponding to this, like e raised to x equals to n equals to 0 to infinite. This is x equals here, it's 0 power of n, means the value of n is 0 here. So n equals 0 to infinite x n over n factorial. This is the exponential series. Similarly, we can follow this procedure for all the trigonometric functions. So here right now it's compact. We don't need to write all the terms here. And this procedure can also be followed for typical differential equations or like special functions, as I have taken an example of special functions here. The Lagrange function. This is the differential equation corresponding. Let me show. X y double dash plus 1 double prime plus 1 minus x y prime plus n y equals to 0. N is the integer. This can run from 0 to infinite. So there will be infinite differential equations corresponding to this general differential equation. We need solution for all of them. And it's not possible to memorize all the terms from 0 to infinite. It means the solutions corresponding to all the differential equations. Like if I take n equals to 1, this differential equation is going to be x y double prime plus 1 minus x y prime plus y equals 0. And if we solve it with bounded conditions, we get of Lagrange polynomial, we get y equals to 1 minus x. And for n equals to 2, this equation is here, we'll get 2y, and the solution is going to be this much. For n equals to 3, we are going to have y equals to minus x cubed plus 9 times x squared minus 18 times x plus 6. And similarly, if I do write this for n equals to 7, this is going to be this big expression. The equation is xy double prime plus 1 minus xy prime plus 7y equals to 0. And the solution is minus 1 times x raised to 7, 49 times x6, minus 8, 82 times x5, and so on. Yeah, that is the big expression. Only for n equals 7, and there can be any number from 0 to infinite. So this series would have large number of terms that it's not possible to memorize this and to do calculations with these. So batteries to devise method, which is called generating function. So in compact way we can write this y equals to ln x here. L0x means the solution corresponding to n equals 0 of this differential equation, and ln x equals to 2 means solution of this differential equation corresponding to n equals to 2, as it's here. This is ln 2. So we can write this as ln 0 plus ln 1 like this up to n terms, and there will be infinitely many terms here. And to denote this series, as we can't memorize this and we can't do calculations with if we take these separately, so we write the generating function, and generating function for Lagrange polynomial is going to be this. And it's doubtful, it might be doubtful that for us, those who see this for the first time, that why is t here, as the differential equation is having two variables here. One is independent and another one is the dependent variable y. X and y are there only. Where is this t coming from? There's nothing, no complication about this. This t is just to compare the powers. If there is t equals 0, if n equals to 0 here, then corresponding to this term, there would be a term which would also have t raised to 0 in power. Or if there is another term like L1x t1, that would be compared with the coefficient of t here and t, so that you would get value of n. Similarly, if t square is there, you would take the term which is having t square here. So this is just for comparison, so that there won't arise any complication, like so that we would not compare the term corresponding to order 3 here with any other order here. So 3 should be compared with 3, 2 should be compared with 2, and n should be compared with n, just to keep the sequence. This is here. And then I have written few other generating functions and corresponding to Legendre polynomial this is, and corresponding to Bessel polynomial this is. Similarly, if there would be a differential equation corresponding to, there is a Legendre differential equation. This is having solution p and x for n equals 0 to infinite, and for n equals to 1, that differential equation would have a different solution, and for n equals 2, that would have a different solution, or for any value of n that would have different solution. So if you need you are asked to write the solution corresponding to n equals to m, then you are going to replace this n with m and compare the t mth term here with t mth term here. Then you'd surely have p m x, means the solution of the differential equation where there is n equals to m, you will get from here. And similarly for Bessel, this is t is dummy here just to compare the powers, so that we would not compare any nth order here with n plus 1th or any other order. N should be compared with n. So this keeps the track of the j and x. This would be the solution for the differential equation, a Bessel differential equation, j and x, corresponding to there is n in the differential equation. For j equals 0, this differential equation would have different solution. For j equals 2, it would have different solution. For j equals to 5, it would have different solution, and j equals to n different solution. Just you expand this power and compare the tn with tn here, or t5 with t5 here, and we'll get the solution of the Bessel differential equation for n equals to 5, if n is 5. That is jn5, value of jn5. So this is the way to write the solutions of differential equations, or because when they are in like a series or a sequence of algebraic terms. We can write generating function corresponding to any sequence in any series which follows an order. So this is all about generating functions. Thank you.